All right, so last part, and this is the second optimization. So this is as optimized as we are going to get with quick union, okay? So we now not only have weighted criteria for unioning, for making the root of the smaller tree point to the root of the larger tree, we also have path compression. And what is path compression? Well, remember that find was very inefficient with spindly tree worst case scenario, linear, right? So the way to optimize find is really thinking about, well, the runtime of find is exactly equal to how many times we have to walk up the tree following the parent pointers until we get to the root. That's the runtime of find, right? And so that's why in the worst case scenario where we have a spindly tree where we need to walk up n parent pointers, our runtime is going to be theta of n. So how do we decrease that runtime? Well, it has to be with having an easier direct access to the root, right? And so that's the whole idea behind path compression. So if we take a look at this example, we already know that we can actually union 0 and 6 from previous parts. And the really important thing here is that when we call, so union of, let me break it down a little bit further. So 0 of 6, when we call the union of 0 and 6, the first thing it's going to do is it's going to call find of 0 and find of 6. Okay, it needs to get these values to see if it can actually union them, because if they're in the same set, if their find return the same value, then there's no reason for us to union. Doesn't make sense. Okay, so by find of 0, it doesn't have any parent pointers, so really it's not going to contribute much to our runtimes. That's okay. But find of 6, notice that we're walking up this parent pointer. We're also walking up this parent pointer to get to the root. So why not make our life easier the next time we need to call find on 6 by actually changing the parent pointer of 6. Okay, so we're going to delete this entirely and have it instead point to the 3 directly, because we're already walking up this path, right? We're already walking up from 6 to 5 to 3. So if we're doing that work already, why don't we just make our life easier the next time we repeat that work, okay? And so that's the whole idea. And so the resulting tree is going to look like this. And again, we're going to be using the weighted criteria. So we're going to have the 0 point to the 3. Okay, so nothing changes in this set. But now for the 3 set, the original 3 set, we have everything at the next level of the root, okay? And so think about it, right? The next time we call find of 6, what do we have to do? We only need to walk up this one parent pointer, right? That's better than having to walk up 2 parent pointers, and it's especially better than having to walk up n parent pointers, right? If our 6 was all the way down here, and these are all other nodes, and our 6 was all the way down here, while we're still walking up all of these parent pointers very painfully, why don't we make our life easier by just having it point directly to the root? And in fact, we can have all of these nodes also point directly to the root, okay? So I know this is a pretty messy diagram. Basically, you will not have any of these pointers anymore. The direct parents of all of these intermediate nodes from the find node on its path to the root are now going to have its parent pointers changed as well, because you never know when you will call find on those vertices too, right? Okay, so that is my little spiel on find, on path compression. And so with this new tree forest, okay, what is our array representation going to be? Well, 0 is going to have its parent be 3 now, 1 and 2 are 0, and then 4, 5, and 6 are all 3. And 3 is now going to have -7 as usual.